Today we will be covering astrophysics, specifically the relationship between spacetime and gravitational waves. So, what is spacetime? You might assume it's something from a science fiction world, but spacetime is just what it sounds like. It combines the planes of space and time. Think about it this way. When you make plans with friends, you set up both a time and a place. The way we experience the world is through this lens. This experience is what physicists call spacetime. It's fusing space, which is 3D, and the 1D concept of time into a 4D plane of existence. Weird, right? So how does this relate to gravity? Well, when Newton came up with his famous laws of physics in 1687, he couldn't figure out the why of gravity. He defined it as a force, and though this works just fine for Earth-level physical interactions, it doesn't explain all the observed anomalies out in space. To address this, Albert Einstein published his famous theory of relativity in 1915, which attempted to fill in the gaps. Einstein described gravity as the curvature of space-time. The more massive and energetic something is, and the more momentum it has, determines how much space is curved or distorted around the object. Einstein believed that this gives us the force of gravity, the resulting curve of space-time around objects in space. So, how did we prove it? The proof is in something called a gravitational wave. Let's break it down. We now know that gravity is the curvature of space-time. So what would a gravitational wave look like? Think about it as a stone dropped in a pond. The resulting ripples distort the water. Now take that idea and imagine two black holes merging. That type of collision is bound to cause some waves. Black holes' gravity is so strong it pulls in even light. So if you have two of them, that's a lot of space-time curvature. Waves of gravitational disruptions fly out during this merger process. So, what would this look like on Earth? The truth is, you wouldn't even notice. These waves stretch the fabric of space itself, creating tiny differences in space, nearly fractions of an atom's worth of distance. 100 years after Einstein's theory was published, we observed one through NASA's LIGO observatory. It's set up with mirrors and lasers, and the highly sensitive instruments recorded that space itself stretched and contracted ever so slightly. These waves came from two black holes running into each other over 1.3 billion years ago. This was the proof Einstein and countless scientists were looking for.